All right, well, hey, welcome to week 3 of Trig. We're moving right along, huh? Today's plan, we're going to go ahead and go over the quiz that you guys took last time, and then we're going to pick up where we left off, which is basically looking at these things, these trig functions as functions, and talk about their properties. And we'll start drawing their graphs. We'll actually start looking at what the graphs of sine and cosine will look like. All right, so that's my plan. But as always, before I do my thing, I do want to turn it over to you guys and see if there are any questions from homework or anything that you'd like to talk about. Go ahead and throw them in the chat box or speak up. All right, so it's looking like we don't have anything right now. So let me go ahead. I'm sorry, go ahead. Anna, were you going to say something?
Yeah, actually, sorry. Took me a second to find the mute. Could you possibly go over question 8 on section 7.2 of the homework?
Sure, 7.2, number 8. All right, I got that on my list. All right, well then let's go ahead and take a look at that, and then we'll, if anything else comes up, if you guys think of anything else that you want to talk about, just throw it in the chat box or chime in and let me know. But let me go ahead and share my screen, and we'll go take a look at number 8. All right, so a surveying team is trying to estimate the height of a mountain above a level plain. From one point on the plane, they observed that the angle of elevation to the top of the mountain is 25 degrees. From a point 2,000 feet closer to the mountain along the plane, they find that the angle is 29 degrees. Figure out how high in feet is that mountain. Okay, so let me just write down the pertinent information here real quick. And I'm going to go ahead and share my whiteboard, and we'll see if we can work the sucker out. All right, so I'm a huge fan of drawing the pictures. Help us see what's going on. So we got our level plane, and then we got the mountain. So we know it's a mountain because there's some snow on top of it. Okay, so what we know is that they are standing at a point out here, and they measure the angle to the top of this as 25 degrees. And then they move a little bit closer and measure to the top, and they find that that is 29 degrees. Other information they tell us that that was a distance of 2,000 feet that they moved in closer. And finally, we're trying to figure out this height, right? So like if we imagine that the plane continues. All right, so there's all our information in a picture. I'm a huge fan of this because I'm really visual, helps me see things, helps me get stuff organized a little bit. And that way I'm not like seeking through words and all that. All right, so I don't know about you guys, but I definitely see 2 triangles here. You see the one with the green line. So we have this triangle, 29 degrees with H. And then we've got the other one, also with H. But this is 25 degrees. And we know that somewhere in here is 2,000 and a little bit more. All right, so let's just think about what we need. If we're going to figure out the height, given some angles here, what else do we need? What other information do we need to have in order to calculate that height? Well, how about this? Do we have enough information right now? Like think about this triangle right here. If I wanted to calculate h, do I have enough information to do it?
No, we need another length, right?
Okay, so correct. We would need another length of some kind. All right, so unfortunately, we don't have enough information to do that here. And then if we come in, we look on the other side, or the other triangle, we have sort of the same situation, but we're closer. If we knew the entirety of this bottom side, we'd be good. Because then we could use tangent, right? Because tangent is opposite over adjacent. And so we could use our tangent to calculate that. So while it's great that we know that this piece is 2000, I really need to know how big the other piece is. So I'm just going to put a placeholder in there for now. We'll just call it X. Because if I have that, actually, let me come back and show you where that is on this picture. That would be this distance right there. But if I had that, then I could calculate h. Because I know that the tangent of 25 is equal to h over 2000 plus x. So you get me x, I can calculate h. All right, well, let's take a look at where that x is. And let's put that into the other triangle. So that's this guy down here. So this one's got that side x. So basically same thing here. If you tell me what x is, I could also calculate h here, because I know that the tangent of 29 is going to equal h over x. All right, so regardless, you get me x, we're good to go. All right, well, yay. We know we need x, but how are we going to find x? Well, this is where we're going to use some algebra. How many unknowns do I have right now? How many different letters do I have in here that I don't have values for?
2.
2, right? H and x. All right, so if I've got 2 unknowns, how many equations do I need to calculate h and x? Think systems.
Do you need 2?
We also need 2. All right, so forever, in any situation, you have a bunch of unknowns, you need that many equations to solve using a system. And so we've actually got that, right? Here's equation 1 that involves h and x, and here's equation 2 that involves h and x. So what we can do is we can solve for one and substitute it into the other. All right, so for example, I'm going to take this first equation and I'm going to solve it for h. Just bring this up here. So I got h equals x times the tangent of 29 degrees. Just multiplying both sides by x. And now I can take this I can put that in there for h. And so what this equation is going to look like is tangent 25 degrees equals x times tangent of 29 degrees over 2000 plus x. And now that's an equation that's only in terms of x. And we can solve that. So since I've got a fraction, let's get rid of that fraction. Let's multiply both sides by that 2000 plus x. Now I'm going to distribute on the left-hand side. So I get tangent of 25 times 2000 plus x times tangent of 25 equals x times the tangent of 29. So I've got more than one x. So the trick with that is to move them both to one side. So I'll go ahead and move those both over to the right-hand side. That way I only have to move one thing because I'm lazy. And now we get to do the dreaded F word. We have to factor. We have to factor out that x. So we've got 2000 tangent 25 is equal to x times tangent of 29 minus tangent of 25. And then we can lastly, 2000, divide by that factor. Whew. All right, so systems of equations. Don't forget about systems of equations. Please, please don't forget about that because you're going to use them in calculus a lot. There are lots of situations where we have more than one thing that we don't know. And we have to be able to go back and find those things. So always get as many equations as unknowns. Well, anyway, now we figured out what x is. And you may remember that at the very beginning, we said, well, if we know x, we can actually calculate our height. And that's absolutely true. So whatever that number is that you get for this, right? So you're going to punch that in your calculator. Make sure you're in degree mode since those angles are in degrees. You can take that and put it up into this other one where we have our h equals. And that will get our height. So it turns out we did have enough information in a roundabout kind of way. All right, so is that good, Anna? Is that kind of what you were looking for?
Yep, thank you very much.
All right, you're welcome. All right, any other homework questions? Oh, all right. Okay, well then, before I jump into new stuff, we're continuing our conversation about the trig functions. Let me go ahead and just go over the quiz real quick. So everyone's should have their scores in there. If you don't, please let me know, because there's possibility that you send it in an email or something, and I kind of missed that. But just a couple of things in general. Number one went pretty well, the conversion. Really the only issues with that was the reduction of the first fraction. Actually goes all the way down to 7 pi over 30. You can divide both top and bottom by 6. And then the biggest issue on 1B was forgetting the minus sign. Since it was a negative radian angle, it's a negative degree as well. And on degrees, make sure that you put the little degree symbol, you know, kind of like I have here on the board, on the whiteboard, because without a degree symbol, it's a radian. And there's a huge difference between, say, 29 degrees and 29 radians. I didn't take points off for that, but I probably made a comment if you didn't do it. So keep in mind, make sure you always put that if it's degrees. So number 2, the one where you where I ask you to find the area of the circle of the sector. All right, so the area is 1/2 r squared theta, but it's super important that this be in radians. And the angle I gave you was in degrees. So what you need to do is convert that to degrees first. So we had 73 degrees. Well, that's going to be 73 times pi over 180 radians. And so that's what you're going to put in for your theta. So I think the radius was 4, if I recall correctly. And this is what you need to calculate to actually get the area. So just watch out for that one. Radians, 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 radians. In number 3, we had this right triangle, and we had side lengths 7 and 8. There's our guy theta. So first things first, if you're going to find the trig function values, you got to find the third side. And the third side, we're going to get that from the Pythagorean theorem. So we get a squared plus 49 equals 64. So a squared equals 15, or a equals the square root of 15. So that's that side length. So then, now that we know that, we can go ahead and get our trig function value. So I don't think I'm going to write them all out, but we'll at least find the big three. All right, so sine is opposite over hypotenuse. And this one, people definitely had trouble with which side was opposite. Think about theta, the side that's opposite it is actually the 7, right? It's the opposite side of this triangle from the angle theta. Now, if you go back and you look at your notes and you go, well, wait a minute, when we did it before, the horizontal side was the adjacent side. Well, that was because we had a different angle. We had the angle that was down here. So it's not horizontal or vertical or anything. It's just think about in the triangle, which side is on the other side of the triangle. That's your opposite. So that makes the square root of 15 our adjacent, and the 8 is our hypotenuse, because that's the long side. Hypotenuse is always the long side. All right, well, now we can get all of our values. So sine is going to be 7/8, opposite over hypotenuse. Cosine is going to be square root of 15 over 8, adjacent over hypotenuse. And then the tangent is going to be 7 over root 15, opposite over adjacent. If you can leave it as 7 over root 15. I don't care if you rationalize in this class. If you want to rationalize, that's fine. That's 7 root 15 over 15. And then the other three are the reciprocals. Let me just go ahead and get them here. So cosecant is 8/7. Secant is 8 over root 15. And cotangent is root 15 over 7. All right, so just a couple of things again. Remember, you got to use the quadratic or the Pythagorean theorem to find that third side. And then be really careful labeling specifically opposite and adjacent, because if you get those mixed up, then all of your trig functions are going to be off. A couple more things just about this in general. Leave it as square root of 15, please. Do not write it as all the crazy decimals. Because as soon as you put decimals there, you're approximating it. The square root of 15 is a number. It's no different than the number 2. You guys just don't like it so much because you're not familiar with it, but to a mathematician, that is the answer. So the answer to sine of theta equals 7/8, or sine, the answer is, for example, of cosecant of theta, it's 8/7. It's not 1.1 blah, blah, blah. Because even if you include 1,000,000 decimals, you still don't have them all when you deal with things like radicals. Okay, so leave them like that. The other thing, some of you tried to put these answers or type these answers on like in a Word doc and stuff like that. And that's totally cool, but let me just show you what the convention is when we type these things. If you want a square root, let's say you want to do square root of 15, you type that in as SQRT of 15. If you want to show, say, a squared, you type a and then the caret. That's the thing that's on the 6. You do a caret 2. All right. So kind of the standard is, this is for exponent. So anytime you have an exponent, sorry about that. Got a little button that's getting in my way. There we go. So that shows an exponent. So even if you have like e to the x, you would type it as e caret x, right? And then again, square root is just SQRT. All right, so that's the standard. For a couple of you, I had to try to figure out what you were saying and doing there, but this is what we do. Okay, and then lastly, number 4, I think just about everybody did fine on this, but real quick, here's the picture. So we're trying to figure out the height of the flagpole. We know that the shadow is 2.5 meters long, and we've got an angle of 41 degrees. If this looks familiar, it should. This is very much like the homework problem that Anna asked me about with height of the mountain. So for this one, we can do the tangent of 41 is equal to h over 2.5. And so h is just 2.5 times the tangent of 41. But again, make sure your calculator's in the right mode. You should get a number around 2.17 meters. If you were getting a number like 0.4, that's because you were in radian mode instead of degree mode. All right, so there's quiz number 1, and those scores are in the book. So while we're talking about quizzes real quick, I decided to change our schedule a little bit for this class. We were set to have our first exam on Wednesday, as in 2 days. I don't want to do that. We haven't talked about enough stuff yet for an exam. So instead of an exam on Wednesday, we're going to have a quiz on Wednesday. So quiz 2 is going to be on Wednesday. And exam 1 is going to be next Wednesday, April 28th. So I just swapped those. So quiz 2 and exam 1 have been swapped on our syllabus. I've also changed the dates on Canvas. So you should see those. I will send out a Canvas message as well. But just so you guys know, the first exam is next week. Next week is our first exam. Okay. All right. So let's keep talking about the trig functions and what we see with them and all that. So give me 1 second. I'm going to hop up to my whiteboard and we'll keep talking about specifically sine and cosine. All right. So we've been fiddling around with sine and cosine and tangent, all these trig functions. And we started by looking at them on right triangles, but then we went to the unit circle. Let me just really quickly remind you what that looks like. So if we're on the unit circle, and that's actually very important, the unit part of the circle is very important. But if this is a unit circle, meaning radius 1, then the coordinates of the point tell us all the trig functions, right? So given some point over here that's x, y, we've got the sine is y, cosine is x, tangent is y over x, and so on and so forth. Okay, so when we're on a unit circle, we can get this. And so we kind of toured it. We found all those special angles. We made that big chart. But I want to get us away from looking at the unit circle a little bit, because we're not always on the unit circle, right? We're not always on a unit circle, and sometimes we're not even talking about something that seems to be circular when we're dealing with trig functions. So we need to kind of expand ourselves off of that. So first things first is suppose that we have a point that's not on the unit circle. It turns out that we have to adjust things slightly, because the sine now isn't just the y coordinate. The cosine isn't just the x coordinate. We have to do things a little bit differently. And we have to scale for the fact that we're not on the unit circle. So like, let's say our circle had a radius of 5. And we had some point out here. Actually, we'll just go, let's say that this is a radius of 2. So whatever those x and y coordinates are not going to be the sine and the cosine, because the sine and the cosine are actually going to be coming from this orange dot that's on that same unit circle. So we have to scale ourselves, but it's really easy. You just have to divide by the radius. So now the sine of theta is going to be y over r, and the cosine of theta is going to be x over r. So by dividing by the radius of the circle, you adjust it so that now you're on the unit circle. And then it's super easy. But even better though, tangent's awesome because tangent turns out doesn't change. It's still y over x. It's still going to be y over x. And that's because if you were to take these 2 points, the ones that we adjust in terms of r, and divide them, when you flip and multiply those, r's end up canceling out. So tangent doesn't care actually at all where it is. Your point can be wherever. You just take y over x. You'll get your tangent of theta. All right, so just realize that if you're not on the unit circle, that's all you've got to do. So a real fast example, because it's pretty straightforward. Let's say that we've got a point 1, 3, and we want to get the sine and cosine and tangent and all that for this thing. So what we have to figure out first is what our radius is. Well, the way that you find your radius, let me just put this point on a graph. So we've got the point 1, 3, somewhere over here. Right, we're going to go over 1 up 3. So if you want to know your radius, you just have to figure out that length. And that length comes from the Pythagorean theorem. So r squared is going to equal 1 squared plus 3 squared. So r is the square root of 10. So then we can get our trig function values. Sine of theta is then going to be 3 over the square root of 10. We have to take that y coordinate and adjust for our radius. And the cosine is going to be 1 over the square root of 10. And then the tangent is lovely because it's just 3 over 1 or 3. We don't actually have to worry about that. So if you end up not on the unit circle, don't let it throw you. Just realize that all you have to do is retreat a little bit. And that's, you do that by dividing by your radius. You just scale it. All right, so not that big of a deal. All right, so we've defined them all in terms of the unit circle. And I really want to start just looking at them as functions. And we did this last time. We started looking at sine and cosine. And so let's sort of continue that discussion. So here's where we got last time. We're going to look at a couple of functions. One of them here is sine of theta. And then another one we were looking at was cosine of theta. And we had gotten to domain and range. Okay, we saw that the domain for both of them was all real numbers. Meaning, you can plug anything you want, any angle you want in for sine or cosine, and it's going to be defined. Basically, think about how sine and cosine are defined as the x and y coordinates of a point on the unit circle. No matter what our angle is, you can keep spinning in any direction, however far you want. The terminal side will always intersect the unit circle, which means there's always going to be a sine and a cosine. And then we saw that the range, though, was restricted. We only got values between plus and minus 1. But that makes sense graphically, at least it should. Think about that circle. The x coordinates on that circle are always going to be between plus and minus 1. You're never going to go further to the left or to the right of the unit circle than plus or minus 1. And the same thing for the sine, which were the y coordinates. Those things were between plus and minus 1 as well, because the y coordinates were trapped between plus and minus 1. Okay, so we've got domain and range. But there are some other properties of functions that I want to discuss with these guys. And the next one I want to talk about is even and odd. So, quiz for class. Just in general. What does it mean when we say that a function is even? Does anybody remember what that means?
Isn't it the way the arrows point at the end? Like odd is up or odd is opposite, evens together.
Okay. So Jack, thank you for that. That's definitely part of it. When we talk about an even function, like if an even function is going up over here on the right, has to be going up on the left or down and down.
Oh, so is it the number that's gonna, yeah, the like to the second or third or fourth or something like that?
Okay, so it gets those names by looking at power functions. So x to the power. If that power is evens, like x squared, x to the fourth, x to the sixth, those things are all even functions. And then the odds, obviously, if you have odd powers, x to the first, x to the third, x to the fifth, those are also odd functions. So that's how they get their name, but there's a little bit more to it than just that, because you don't have to have, say, x to a power for a function to be even or odd. Anybody remember a little bit more to that? But thanks, Jack. That was really good. I'll give you a hint. It has to do with negatives. Does that bring back anybody's recall? All right, well, here's how it works out for even. If you plug in a negative, you get exactly the same thing as if you plug in the positive. And so an example of that would be like x squared, because if you take 4 squared, you get 16. If you put in -4, square it, you also get 16, right? The plus and minus give you the same value. So that's what it means for a function to be even. For a function to be odd, if you plug in the negative, you get the opposite of what you would get if you plugged in the positive. And something like x cubed is a good example, because like if you take 2 and cube it, you get 8. If you take -2 and cube it, you get -8. All right, so that's the definition of even and odd. All right, so even functions, you get the same thing if you plug in the negative. Odds, you get the opposite. All right, well, it turns out that sine and cosine are examples of both of these. One of them is even, and the other is odd. So let's see if we can figure out which is which, and we're going to use the unit circle to kind of help us again. So let me draw a unit circle here. All right, now let's think about sine and cosine in terms of the x and y coordinates, but let's think about going in a negative direction. So I'm going to give you a regular old theta. So let's say that this is theta. Let's think about negative theta. Negative theta means we go the opposite direction, but the same distance, same rotation. Okay, so let's think about these 2 points. Now, I'm just going to call this guy generically x comma y. What would the coordinates be of the other one?
Would it be negative x and, wait, no. Would it just still be x and y?
Okay, so the x coordinate is going to be the same x coordinate, right? Both of them have moved the same distance left and right. So the x is the same. But what about the y?
That would be negative.
That's the one that's negative. Yeah, because now that one's below instead of above. So if we go in the opposite direction, we're going to get the same x coordinate, but our y's are going to have different signs. Okay, well, so think about this then. A function is even if when you go the other direction, you get the same value out. Well, the one that's the same is x. So that means that cosine of theta, this is an even function. That's even. If you go the opposite direction, you're going to get exactly the same value for the x coordinate. And the x coordinate is your cosine. So that's kind of cool, actually. So all the stuff that we know about even functions, like specifically the symmetry of even functions, we're going to be able to use when we draw the graph of cosine, which we're going to do in just a little bit. All right, well, the x coordinates stayed the same. The y coordinates changed sign. So that means that the sine function is odd. Because we don't get the same value, we actually get the opposite value, opposite in sign. All right, so even though they're not polynomials, they're still even and odd. Just using the definition of what it means when we plug in negative. All right, so even and odd. Another property that these things have that you probably have not seen yet with other functions is the fact that they repeat, right? Like if you look at the chart, say for cosine or sine, go back and look at our angles. You know, we started at 0, an angle of 0, and we worked our way down all the way to 2 pi. And by the time we got to 2 pi, we got the same value. And if we were to continue our chart, it would just be a copy of what we saw before. And that's because of the fact that if I spin around, we did basically one full rotation, right? From 0 all the way to 2 pi, but I could keep going. And I'm going to be coterminal with those other angles and get the same values and then keep going. And like, think about this green arrow right here. I'm going to intersect this circle with this angle an infinite number of times. I just have to keep spinning, but they always occur in the same pattern at the same frequency. And when we have that, that's a property what we call a periodic function. So let me write here. This is a definition for you. So periodic function is a function that repeats at a constant rate. So you're going to see a repetition, and that repetition always occurs over the same interval. And we define the shortest interval we call this the period. So when you have a periodic function, something that repeats, the period is the shortest amount of time that it takes for that repeat to happen. And both sine and cosine are periodic, and their periods are 2 pi. Okay, so every 2 pi, we're going to get the exact same function value. I wrote here period function. I was supposed to say periodic. Sorry about that. Periodic function. Now, mathematically, what we write when we want to talk about a periodic function is that f of x plus the period equals f of x. Right? So whatever the period is, you just get the same thing. So in terms of sine and cosine, the way we would write it, this fact mathematically, we would say that the sine of theta plus 2 pi is equal to the sine of theta. And similarly, the cosine of theta plus 2 pi equals the cosine of theta. Now, what this is going to mean for us, like why we care about that, is it's going to make it so that we have less to remember. Like if you know that chart for sine and cosine, you can just copy it and do it for the next cycle and the next cycle and the next cycle and the next cycle. We don't have to learn anything new because every 2 pi, it just repeats, right? So periodic functions, they're the Groundhog Day of functions, right? I'm sure you've seen the movie or know the movie with Bill Murray, right? Where you just every day, same day, same day, same day. Okay, periodic functions are those. Like, haven't we already lived this before? Yep. 2 pi ago, you saw this, and you know what? In 2 pi, you're going to see the same thing again. So they just repeat over and over and over. Now you're going to see that not all trig functions have the same period. There are others that have a different period, but they all repeat, which should make sense because of the fact that we're getting them from a circle and we're just spinning around the circle over. Okay, so there are a couple more properties for these functions. We're going to add to this list, though. We're going to talk about other things, specifically those that involve their graphs. So let's just start there. Let's start by drawing a graph of cosine. All right, so I'm going to start with cosine. I know the book starts with sine. I prefer cosine. Cosine's my favorite of the trig functions. Yeah, I know that's weird to say I've got a favorite trig function, but it's cosine. Cosine's by far the superior trig function. But we're going to start with a graph of cosine, and then we'll turn our attention to sine and all that. All right, so to do this, let's go ahead and just do the old point plotting method that you guys are used to. You remember the good old T-charts, right? You plug in your X's and your Y's, you get your points and all that. Okay, now we're going to draw a graph of cosine, but I want you to understand that this x-axis, this is actually going to be a theta axis. So we're plugging in angles. And then on this axis, I'm going to call it just f of theta, because I don't want you to think about it as y and x. Because then when we talk about the unit circle y and x, you're going to get confused. Okay, so when we talk about y and x, we're going to be talking about the unit circle coordinates. On this graph, it's going to be thetas and f of theta. All right, so let me give myself some tick marks here. Now, vertically, I'm going to make these things halves. So every one of mine is a half. And then horizontally, I'm going to do pi over 2s. Okay, so this one is pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, and so on. And then in the other direction, of course, this is minus pi over 2, minus pi. All right, so that's my scale for my graph. So what we're going to do is we're going to go ahead and plot cosine. So we're doing f of theta equals cosine of theta. And so we're going to use a t-chart. But here's the beautiful thing. We already have that t-chart. Remember that big chart we filled out last week? That's our t-chart. Those are our angles and our trig function values for those angles. Okay, so here's what we're just going to start at the very top of that list, top of that chart. So hopefully you have that handy. It's probably a good idea to have it always with you when we're learning this stuff until you get it down. But at an angle of 0, we saw that the cosine was equal to 1. So I'm going to go ahead and put a point here at 0, 1. Let me go ahead and get the values for the nice angles on my where my scales are. At pi over 2, so if we go down our chart to pi over 2 and you look over, under the cosine column, you're going to get 0. At pi, you're going to get -1. At 3 pi over 2, we had 0. And at 2 pi, we were back up to 1. Okay, so those were the every fifth one on our chart. Okay, now I need to get the others. And for the others, let's at least use decimal approximations so we can get them roughly where they need to be. Obviously, 1/2, we know where 1/2 is. √2 over 2, that's right around 0.707. And then √3 over 2, that's around 0.866. So you can just use your calculator to get those decimal approximations. Again, remember, decimals are approximations. But for drawing my graph, that's going to be, knowing it's 0.7, I'll be lucky to mark 0.7 exactly on my graph, let alone 0.707. So, but at least it gives us ballpark where we need to be. All right, so let's get the other points and let's look in the first quadrant. So the very top of our chart. So the first one was 0, an angle of 0. The next one was angle of pi over 6. And pi over 6, that's 1/3 of the way to pi over 2. That's right here. And I get a y value of √3 over 2, which is 0.866 something. So that's going to be this point right here. So that's the point pi over 6, √3 over 2. Okay, so then we go down the next one. Pi over 4, that's halfway to pi over 2. And we get √2 over 2, which is 0.707. I'll put that dot right there. That's this guy, that's pi over 4, √2 over 2. And then we get pi over 3, and pi over 3 is 1/3 of the way to pi, so let's get that there. And we get 1/2. So we draw that point. So I'm just using the values that we had already calculated to draw my dots, because I'm going to do the old draw the dots and connect them. Okay, so keep going. When we move to the next guy, 2 pi over 3, we're going to get -1/2. 3 pi over 4, we get -0.707. At 5 pi over 6, we get the √3/2, so 0.866. At pi, we got -1. Then we get the minus √3/2, minus √2/2, minus 1/2, 0. Then we get the plus 1/2, plus √2/2, plus √3/2. So there are all of the points from our chart. So now we connect the dots. And what we see is something that looks like this, more or less. All right, so at least between 0 and 2 pi, we know what we see, because we have those values already. All right, well, now let's make use of the fact that this is periodic. So periodic just means that it's going to repeat the same thing if we keep going. So think about this. Once we get to 2 pi, it's going to repeat and start doing the same thing. It's going to drop back down to 0. And then once it's at 0, it's going to drop back down to -1. And then back up to 0, then back up to 1, then 0, then -1, then 0. Then it's just going to keep going. And the same thing if we go backwards. If we go backwards, we're going to repeat. So we're going to see something that looks like this. All right, so there you go, folks. That's the graph of cosine. This is the function f of theta equals cosine of theta. So remember, when we draw graphs of functions, we're just drawing graphs of input-output pairs. Okay, so on this horizontal axis, that's the angle we're putting in. And on the vertical axis, that's the number that comes out. All right, so if you had to name the shape, what would you call that? Oh, come on, name it. What's it look like to you? There's no wrong answer here, by the way.
A snake.
Okay, a snake. I've not heard that one before. That's cool. Thanks.
Looks like a parabola, almost. I don't know.
Looks like a parabola.
Yeah,
Except don't parabolas like go down or go up forever?
that's true.
So I don't know that I'd want to call it. Maybe a wave.
Yeah, it looks like a wavelength.
Yeah, like maybe like a wave. That's kind of what I was hoping you guys go for. So we call this a wave. This function, this graph is actually called a wave. The shape, it's actually called a sinusoidal wave. That's the actual name for it. It's a sinusoidal wave. I'm sure it's going to come as no surprise to you guys that the graph of sine is also going to give us a wave, and that's how it gets its name. Right? It's a sinusoidal wave. Okay, so now let's take a real quick pause here. So remember what we're studying, right? We're studying triangles, trigonometry, and yet that led us to dealing with circles, which now is leading us to waves. Yeah, that makes sense. Okay, to me, this is the beauty of trig. Trig is all over the place. And in fact, if you want to describe anything that's got a wave-like structure, you use trig, you use sine and cosine. And so for those of you who are going into the sciences, into like physics or engineering, you use this for physical waves, like ocean waves, waves on the lake. But you also use it for sound, because sound travels in waves. You also use it for light, because light travels in waves. We have all kinds of things that we use this for, because the wave-like nature of life. There are so many things that are periodic, that repeat regularly, that lead to this kind of thing. All right, so there's a graph of sine or a cosine. So think about what we saw. We saw before that the domain was all real numbers. So on a graph, that means that this graph extends forever left and right. And it does, it just keeps going, same pattern. The range was between plus and minus 1, and you can see that on this graph as well. Everything is trapped between plus and minus 1. This graph never goes up above it, it never goes down below minus 1. That's always stuck in between. We also saw that it was periodic. Yeah, you see that, it repeats. But we also saw that it was even. Now, another thing I want to remind you about even functions is that they have symmetry. And even functions are symmetric over the y-axis. Meaning if the y-axis is a mirror, the vertical, not y, the vertical axis. So if this vertical axis was a mirror, you see the same thing on both sides. And while I didn't draw a lot over here, and I'm not going to go much further because at home, if I write on the walls, I get in trouble. If I'm at the college and I write on the walls, they go, oh, of course, that was Bruce. So I'm not doing it. But if I were to keep drawing this, hopefully you can see the mirror image. You can definitely see it here, right? It's exactly the same y values as I'm moving in the opposite direction. That's what I meant to be even. When you go negative, you get the same thing as if you go positive. All right, so all of those things that we saw, those properties we saw, are manifesting themselves in the graph. But now that we have the graph, I want to talk about some other things that we talk about with graphs of functions. Some other things that are important are like intercepts. So maybe let's start writing a list of some other things that we recognize about this. How about the y-intercept? Where does this thing cross the y-axis?
At 1.
At 1, right? So we know that the y-intercept is 0, 1. When it comes to x-intercepts, there are more than one. In fact, there are an infinite number of them. Right? We got 1, 2, 3, 4, 5, 6, yeah, and they just keep going forever. So it turns out that there are tons of them, but they all follow a pattern. I mean, look at the numbers: pi over 2, 3 pi over 2, 5 pi over 2. The next one in that pattern is odds on top, would be 7 pi over 2, then 9 pi over 2, 11 pi over 2. Same thing in the other direction, minus pi over 2, minus 3 pi over 2, minus 5 pi over 2, and so on. So the way that we're going to write this is we're going to write it as pi over 2 plus n pi comma 0. Now, you may not have seen this before, so let me just kind of play out what this is saying. When I write pi over 2 plus n pi, this n is any integer. We tend to reserve n in math for integers, or natural numbers is where the n really comes from. But basically, this is just saying add your favorite number of pi's to pi over 2. So this pi over 2, this is pi over 2 and no pi's. This is pi over 2 plus 1 pi, pi over 2 plus 2 pi, pi over 2 plus 3 pi, 4 pi, and so on. This is pi over 2 plus negative 1 pi, so minus pi. Pi over 2 minus 2 pi, minus 3 pi, and so on. So because it repeats, because it's very regular, we can write this, and that's what we'll do. All right, so in terms of intercepts, we've got them all now. Y-intercept is at 0, 1, and the x-intercepts, or I guess theta intercepts is what I should call them here. They're all the odd half pies. All right, so those are features of functions that we talk about always. But there are a couple other features of this graph in particular, the sinusoidal wave, that I want to talk about. So check this out. There are maximum values, right? The maximum value is 1, but it occurs regularly. There's a maximum at 0, at 2 pi, 4 pi, 6 pi, and so on. And so it's going to occur whenever your angle is an even multiple of pi. So you write 2 pi n. There are also a minimum value of -1. And this is going to occur when theta is equal to pi, 3 pi, 5 pi, 7 pi, and so on. So the odd half pies. And so the way we're going to write that is pi plus 2 pi n. So the same idea. Take pi and add your favorite multiple of 2. It'll make it so it's always odd. So cosine's kind of cool. At the even pies, we get a maximum value. At the odd pies, we get a minimum value. So it goes max to min, to max to min, to max to min. Just keeps alternating every pi. So some other words you're going to hear me say for these maxes and mins, and this is a lot of people use these words, but I know I probably have a weird combination of them because of the fact that I straddle 2 worlds, that I'm a mathematician who's also a physicist. So I call the bottoms troughs, as in like things that you feed animals in, right? So it's a trough. And then the tops, I call these peaks for obvious reasons. So you'll hear me talk about peaks and troughs, and that's what I mean. I'll also sometimes say maxes and mins. I mean the same thing, max and min, peak and trough. All right, so every cosine's got repeating peaks and repeating troughs. All right, now another quantity we give to sine waves is the total vertical spread. So if you just look at what is the actual distance between the peak value and the trough value, this is called the amplitude. And all waves have an amplitude. All waves have a period, all waves have an amplitude. And in the case of cosine, actually, hold on. So this isn't the, I lied. That's not the amplitude. The amplitude is how far we go up from center. So that right there is the amplitude. So it's the distance from the midline up to your peak. So for cosine, our amplitude is equal to 1. Because the midline is 0 and we go up to 1 and down to -1. So think of amplitude as your deviation from the center. What's the maximum distance you can go from the central value? Well, it's 1. Okay, so there's cosine. Pretty much everything you need to know about it. And we see what its graph looks like. It's just this never-ending wave. We start up here at 0, 1, and then go down and up and down and up and down and up and down. Okay, so there's cosine. So then what about sine? Well, if you draw sine, you're going to see a very similar graph. So I'm going to do this one a little bit faster. Not going to be as precise because I don't really care. It's only sine after all. I care about it. Yeah. All right, so let's do kind of the same thing. We'll put some tick marks on here so we can keep track of what everything was. And do the same thing with the y values from the unit circle or the sine column. So at 0, we had an angle, or angle of 0 gave us a sine of 0. At pi over 2, pi over 2, at pi over 2, we had a value of 1. At pi, we got 0. 3 pi over 2, we got -1. 2 pi, we got 0. If you plug in the respective y values, so you take the sine values and put those in, you're going to see a shape that looks like this between 0 and 2 pi. So just go down that first column on our chart, take those function values, put those in as your vertical, your y's, and this is what it looks like. All right, then we go, oh, but hey, this repeats. Once we get to 2 pi, we're going to see the same thing. So we're going to go up, and then we're going to come down, and then we're going to go up, and then we're going to come down. And same thing if we go the other direction, we're going to go down, and then we're going to come up. All right, so check it out. Here is the graph of sine. And if you look at that and you compare it to what we just drew for cosine, they're pretty much the same. Like, think about the properties, right? It repeats every 2 pi. So it's got the same period. It's got the same amplitude. Got an amplitude of 1, goes up plus or minus 1. What's really the only difference between this graph and the graph of cosine? How do they compare?
Is it that wave again?
Okay, so it's the same wave, exactly the same picture. It's just been shifted. Like, think about cosine. Remember cosine's y-intercept was 1. So I'll draw the graph of cosine in here in green dotted. All right, so the green was a cosine. The pink is the sine. Notice that it's exactly the same picture, just shifted. So if you know the graph of cosine, you know the graph of sine. You just have to start it in a different place, because now when we talk about the intercepts, the y-intercept is the origin. Right? We're going through the origin now instead of starting up at 1, 0 or 0, 1. And then in terms of the x-intercepts, they're at different places. They're at the whole pi's. Right? 0, pi, 2 pi, 3 pi. So they're just shifted off by that half a pi. In terms of the peaks, the maxes now, it's the same maximum value of 1, but they occur at pi over 2 plus 2 pi n. And the mins, well, again, they're shifted a little bit. They're at 3 pi over 2 plus 2 pi. You can see the domain and range again. The domain is everything. This extends forever left and right. The range, we're trapped between plus and minus 1. And you can also see the oddness. With the symmetry, odd functions, they're symmetric about the origin. And what that means is that if you were to spin it, if you were to rotate it, half a rotation, pi radians, 480 degrees, you would get exactly the same graph. So imagine taking this pink and just turning it halfway, you're going to see exactly the same shape. So we even see its oddness when we look at its graph. Okay, so moral of the story, sine and cosine, same graph. They're just shifted. All right, so this also shouldn't surprise you though. You remember cofunction identity? Maybe. Check this out. If you use the cofunction identity and transformations, you'll see why they're shifted by pi over 2. So let me just remind you about this. We knew that the sine of theta was equal to the cosine of pi over 2 minus theta. That was the cofunction identity. Well, let me just do some work on this real quick. I'm going to factor out a minus sign. You'll see why in a second. So I'm going to factor out that negative sign. Now, since cosine is even, that minus sign doesn't matter. Right? Even functions, you do a negative angle, you get the same as the positive angle. And if we think about this as transformations, this is a shift of pi over 2 to the right. It's opposite what you think when you do horizontal shifts. Okay, so basically what this just said is that the graph of sine is the same as the graph of cosine if you shift cosine pi over 2 to the right. Well, the green is my graph of cosine. If I shift that pi over 2 to the right, I get my graph of sine. So their graphs have to have this. They have to have this similarity because of the fact that they have similarity themselves coming from the right triangle. Crazy, 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 crazy. But there you go. All right, so before we move on, how are we feeling about the graphs of sine and cosine? Do they make sense? Are you seeing where they come from? Like all we're doing is connecting the dots. And we're using those dots that we got from the unit circle. So what questions can I answer at this point? Okay, so I'm going to take it that we're feeling all right. Well, let's keep playing with the graphs of these things. But now, let's throw in transformations. So I'm going to write here a generic y equals a cosine of bx minus c plus d. And we're going to look at what do all these letters do? What do A, B, C, and D do to the graphs for cosine? Now I'm doing this for cosine. Same thing's going to happen for sine, because remember, it's just shifted. So if you look at one or the other, sine or cosine, you'll know what happens with the other one. I'm going to show you cosine because the book goes through sine, right? But it's the same idea. All right, so how well do you remember your transformations from pre-calc? You were taking college algebra. And I'm totally cool with honesty. If it's crap, if it's garbage, just say no. Don't remember. I mean, that's totally fine. Do you at least remember transformations existed?
Yes.
Yeah. Okay, cool. I'll take that. All right. Well, all of these, A, B, C, and D, are all going to lead to transformations of some kind. Okay. The A is being multiplied, right? And when you have multiplication, that's a stretch and compress. And because it's outside of the cosine, this is going to be a vertical stretch or compress. Meaning, think of the graph as something made out of something elastic like rubber or whatever, and we literally just stretch it, or we push it down and compress it. Okay, but that's what that A is going to do. That's going to be a vertical stretch or compress. Now the B is also a multiplication. Right, it's B times X, but it's happening inside cosine. So that means that it's going to be a horizontal stretch or compress. So same kind of deal. It's just now we're going to either stretch it horizontally or compress it horizontally, depending upon what that B is. So multiplications, those are stretch and compress. Inside is horizontal, outside the function is vertical. Okay, now the C and the D, they're being added. I know you see this as subtraction, but by this point, you should be okay with subtraction as adding. Because it is, it's just adding a negative. So you're going to hear me all the time. When there's subtraction, I'll say add. Okay, so don't be all like, oh, technically you're subtracting, because then I'm going to go, no, technically I'm adding a negative. I'll start with. All right, so we're adding C and D. And when you add, those are shifts. Those are pick up your graph and move it up and down. Pick up your graph, move it left and right. Okay, so those two are going to be shifts, but the same thing about are they vertical or horizontal depends on where they are. The D, since it's outside the function, this is going to be a vertical shift. And the C, because it's inside, is a horizontal shift. So that's what those four things are going to do. They're going to take our graph and move it up and down and left and right. It's D and C. And then it's going to stretch or compress it vertically with an A and stretch or compress it horizontally with a B. Okay, so that's what they do. In terms of, is it a stretch or a compression? Well, for the A, if A is greater than 1, this is a stretch. And if A is less than 1 but bigger than 0, we're going to compress it. If it's negative, it also flips it over. That's what negatives do, they're a reflection. Let's not worry about that just yet. Okay, so for the horizontal stretch or compress, we have a similar thing, except it's in reverse. Now, if B is bigger than 1, this is a compression. And if B is between 0 and 1, it's a stretch. Stuff on the inside, the horizontal stuff, it's opposite. It's always opposite of what happens in vertical. All right, so then in terms of the shifts, the vertical shift, it's going to be up if D is greater than 0. And it's going to be down if the D is less than 0. So if we add a positive, then we're going up. We're adding a negative, we're subtracting, we're going down. And then for the horizontal shift, because of how I have this written, it's going to work out that it's the same thing. So that if C is greater than 0, we're going to go to the right. And if C is less than 0, we're going to go left. But that's because we have a subtraction. So think about this, because I wrote it as subtraction. If you see subtraction, you're going to the right. If you see addition, you're going to the left, because adding is subtracting a negative number. All right, so that's what all these things are going to do. So let's think about what they're going to change in terms of the properties of cosine, the things that we've talked about and what we've seen. Okay, so let's just start with one at a time. I'm not going to put all 4 in. Let's just look at one of them at a time, and then we'll start combining. All right, so what is A going to do? So let's say we've got y equals, say, 3 cosine of theta, or cosine of x. So let's think about what that's going to do to our graph. So I'm going to start with a graph of cosine. Okay, so I'm going to do this in a pink and kind of dash it. All right, so there's the graph of cosine. We know that its maximum value is at 1, and its minimum value is at -1. I'm going to change this to a 2 just so I can fit it on my graph. Apologize for that. Make it y equals 2 cosine of x. So now what happens with this stretch compressed is that 2 means all of the y coordinates on this graph get doubled. So instead of being at 1, we're now going to have a point that's at 2. And instead of being at -1, we're going to be down at -2. So all those points are now at 2 and -2. And all the ones that are 0 are still at 0. Because if you double 0, you still get 0. So what we're going to see with the graph of the cosine of 2x is another wave. It just looks like this. So it's a vertical stretch, right? We made it taller than it was before. It's like, you know, the funhouse mirrors. All of a sudden you look taller than you actually are. All right, well, we just made this thing taller. So if you think about all the properties, is it still even? Yes. Right. Does it still have a period? Yes. Is that period still 2 pi? Yes. Still takes 2 pi to repeat. But what's changed here is the amplitude. So we just changed the amplitude, and our amplitude is now 2, because the distance that we travel from the midline to our max or our min is actually 2. We didn't change the x-intercepts, but we did change the y-intercept. It's now 0, 0, 2 instead of 0, 1, but again, because of the stretch. Okay, so that was 2 times cosine. Had it been 5 times cosine, all right, this would have been up to 5 and minus 5. 13 times cosine, up to 13 minus 13. 1/2 times cosine, up to 1/2 minus 1/2. And so no matter what that A is, it's going to change the amplitude. So if we want to make a general statement here, we can say that the amplitude is the absolute value of A. So that's what A does. Changes the amplitude of this graph. It makes it so that it's taller or shorter. That's it. If it's negative, it flips it over. So we would have had a trough at the start instead of a peak. And then it would have gone up and down and up and down. Amplitude is still going to be determined by the absolute. All right, so that's what A does. A changes the amplitude. All right, so let's put in a B. Let's see what happens when we've got some sort of a B here. So let's go with y equals cosine of 2x. So I'm going to do the same thing. Let me draw a graph of regular cosine first. And then we'll see what happens when we put in that 2. All right, let me try to make this a little bit more regular. My other one got kind of squishy, so be good about it. So boom, boom, boom. Okay, so there's our graph of just regular y equals cosine. Hold on a second. I meant to do that in a different color. Okay, so there's regular old cosine. So now let's think about what happens with cosine of 2x. So this is a horizontal compression, meaning the points that we have out here have to get brought in closer to the axis by a factor of 2. We have to cut that distance in half. So, for example, this point that was right here at pi over 2 has to come in halfway to right here. Okay, so that has to get brought in half the distance. This one has to get brought in half its distance, which is right there. The next one comes in half its distance, which is going to be right there. And so on and so forth. So think about that top point comes in halfway there. This one gets brought in halfway, that one gets brought in halfway. And so if I connect the dots now, this is what it looks like. So the x values, let me mark them again. So this was 2 pi. This was pi, 3 pi over 2, pi over 2, minus pi over 2, and so on. Notice that this graph looks significantly different now. It's all been pushed in. So think like a spring that's been pushed in together. So let's think about what properties have changed now. So the amplitude is still the same. It's still going from -1 to +1, so the amplitude is 1. The y-intercept's the same, but the x-intercepts are definitely different. The location of the maxes and mins are definitely different. And in fact, the period has changed. Now this repeats, but it repeats much faster. Instead of having to go all the way to 2 pi to start repeating, now we only have to go to pi for it to start repeating. So this one, it's changed. The period is now equal to pi. So that's what B is going to do. B is going to change your period. It's going to change how quickly it repeats. And in terms of a formula, there's a nice little formula for it. The period is going to be 2 pi divided by the absolute value of B. So the 2 pi should be kind of clear. That comes from the original period. And then we end up dividing by that B so that when it's bigger than 1, it compresses it down. All right, so that's what B does, changes the period. All right, now C and D, they don't change the amplitude, they don't change the period. They just change where our graph is, right? So we don't really have to worry too much about those. We're just going to shift however far. But I will tell you that when we have a horizontal shift, when it comes to sine and cosine, we have a special name for it. And it's called a phase shift. Okay. So horizontal shifts, we call these guys a phase shift. I don't know why, I don't know the historical reason behind that, but we'll talk about these things being out of phase because there's a phase shift or a phase change. But horizontal shifts, we'll call those phase shifts, and then D will be vertical shifts. So I'm not going to bother doing an example of them because I think you can see what would happen if we just had a D, let's say, and we had cosine of x plus 4. You just take that graph and you move it up 4. So the center line isn't 0 anymore, but it's up at 4, but now you just go up and down 1 from 4. Or the same thing if we had a C, we're just going to take that graph and shift it left or right. It's not going to change the amplitude, not going to change the period. It's just going to change where our maxes are, where our intercepts are, things like that. All right, so that's what they do individually. But when you put them together, obviously they do their thing. And the only time that having two of them changes anything really is with the phase shift. There is a formula for phase shift, And I want to go ahead and give it to you here. I'll write it down over here. For the phase shift, it's going to equal C divided by B. Okay, so remember, phase shift is horizontal shift. And so your phase shift is going to be determined by the ratio of those. And the Y behind that is an order of operations idea. Since you multiply first and then you subtract, you have to factor out the B. And when you factor out the B, you find out that what you're actually adding and subtracting is C divided by B. So you can look in the book. I'm not going to go, but you can look in the book. You can go back and look at transformations to see how you deal when you've got both of those going on. But this is how we're actually going to get our phase shift. So if we lump them all together, we can actually keep track of what's going on with our graph and seeing the change in the amplitude period and phase shift. And then we can get a graph of them pretty quickly if we remember our transformations. So let me show you an example. Let's actually get rid of all these A, B, C's, and D's and put in real numbers. But I'm going to reserve our formulas for us for just a second here. All right, so let's go with this guy. Let's say we've got y equals 3 cosine of 4x minus pi plus 1. So here's an example that's got everything in there. So let's see what this tells us. And then we'll put it together into our graph. All right, so first of all, our amplitude is going to be 3. So that means from the midline, we're going to go up 3 and down. The period is 2 pi over b. So the period of this is going to be 2 pi divided by 4, or pi over 2. So this means it's going to repeat every pi over 2. So when we start at 0, we're going to see the same thing at pi over 2. And then at the next pi over 2, the next pi over 2, and so on. So it's happening much quicker because it's been compressed horizontally. Right? Squished it in. All right, and then lastly, our phase shift. It's going to be pi over 4. Right, C over B. And because of the minus sign, I'm going to put here right. I always put right or left when I'm doing my phase shift so that I don't get confused and forget and go the wrong way. I don't like pluses and minuses. In the book, they'll talk about a negative phase shift, positive phase shift. I don't like that. For me personally, I just write out the word left or right. Okay, so there's a phase shift of pi over 2. And then lastly, that plus 1, there's going to be a vertical shift. We're going to go up 1. And the same deal here. I always write up or down, just so that I can remember. All right, so there's all the information that we know about the graph of this that comes from that equation. Now let me show you how we can draw this very quick. All right, so here's what I'm going to do. I'm actually going to start with my vertical shift. All right, so my vertical shift, I went up 1. So what I'm going to do is out here at 1, wherever that happens to be. Hold on, let me put some tick marks on here. I'm going to put a dashed horizontal line. So there's my vertical shift. This is now my center line. The graph of my cosine is going to oscillate around this line. Okay, the next thing I'm going to mark come from my amplitude. My amplitude was 3, which means I'm going to go up 3 from this. And I'm going to go down 3 from it. So I'm going to go ahead and make some more dashed lines here. Because this is the envelope for my cosine. My cosine is going to fit in here. All right, so far so good. So we took care of vertical shift, we took care of amplitude. Let me just mark those real quick. Now I'm going to go to my phase shift. Okay, I'm going to go to my phase shift next. So let me put some horizontal tick marks here. And I'm going to make them so every 2 of them is a pi over 4. Just because this is going to make it so that we can see everything we want. Okay, so I'm going to take care of my phase shift. So here's what I'm going to do. I'm going to go right pi over 4, and I'm going to put what the point should be. So think about cosine. At the axis, it started with a maximum. So that means I want a maximum at pi over 4. It's just my maximum is going to be up on the orange line now. There's another reason I like cosine. Cosine always starts with a max, so it's pretty easy to tell where it goes. All right, so there's my phase shift. Just took care of that. So lastly, let's get to the period. So now the period is pi over 2. So that means that if I go pi over 2 to the right from here, I'm going to be back at a maximum. Well, pi over 2 on my graph is 4 tick marks. So I'll go 1, 2, 3, 4 tick marks. I should get another maximum. If I go right, or if I go left, sorry, 4 tick marks, I should get another maximum. So 1, 2, 3, 4. Go right another 4, or left another 4. 1, 2, 3, 4. Go right another 4, and so on. All right, so that took care of my period. And now all I have to do is finish filling in this graph by knowing what I know about cosine. In between the maxes is a min, exactly halfway. So that means there's a min here. There's a min here. There's a min here. Right? Those minima are happening exactly halfway between the maxes. And they're down on the other orange line because of my amplitude. Between every max and min, every peak and trough, there's a 0, which means I have to hit my central line halfway in between. And when I say halfway, I'm looking at half the distance of the axis. All right, well, there are all my key points, and now I just draw my wave that goes between them. So there is a graph of y equals 3 cosine of 4x minus pi plus 1. And notice that I didn't plug anything into that equation. Didn't plug in a single number. I just made use of what I already knew. I already knew about cosine, and I already know about how all these transformations work. And so there's a graph of 3 cosine of 4x minus pi plus 1. So it's been shifted up, it's been stretched vertically, it's been compressed horizontally, and it got shifted over. So if transformations are a little rusty for you, huge advice is to go back and study them, go back and look at them, because they're definitely going to help you out when it comes time to drawing the graphs of these things. It definitely speeds up the process, and it's what I'm going to model. And so definitely go back and look at that. All right, well, we're out of time for today, so we're going to go ahead and stop here, but I just want to remind you, on Wednesday, we're having a quiz, not an exam. We're having quiz number 2, and it's going to cover sections 7.3 and 7.4. So that's a lot of the exploring of the unit circle and stuff like that. Okay, so quiz on Wednesday on 7.3 and 7.4. And after we take the quiz, after you guys come back at 11:40, we're going to go ahead and kind of pick up the ball and keep running and keep talking about the graphs of these things. And we'll start looking at what about the other trig functions, tangent and cotangent, secant, cosecant. What do they look like? What are their function properties? So we'll kind of do the same thing. All right. So with that, one last reminder is homework due tonight. Don't forget to get in there and work on the sections that are due tonight. But other than that, have an awesome day and go Mariners.
Is the exam going to be